I continue talking about amortized analysis. So last time we looked at one particular method for doing amortized analysis. Can you tell me what's the name of the method? Just to, yeah.
The bank account method?
The bank account method. Okay, cool. Today we're gonna look at just another way to think about this, and you see that it's basically the same, but just with some reformulation. Sometimes it helps you to think about it. Okay, so this is potential function, and just recall a bit like last time, right? Like the bank account method basically asks you this, asks you to design how you can pay, like let's say $C to the bank account on each operation, and you know that like the real cost that occur in the process will deduce $1 from the bank account. But if you can always say that you never have deficit, then you can just from here, you know that the total real cost is just going to be at most C times the number of operations. This is the total amount that you pay. This is the real cost, but you never have deficit. So the total real cost is at most the total thing that you pay. Okay, super intuitive. And you can conclude now that from here you can conclude that if you just need to pay $C per operation, it means that the amortized cost is at most C. Okay, that's the last time. So now let's look at another one, potential function method. And this is really, again, it's kind of a reformulation of the previous one. Okay. But here we'll kind of make things, kind of give some more formalization to it. Okay, so I give some definition. So let's say that CI is a real cost for the ith operation. And phi I, okay, phi I is simply the total amount of money in your bank account right now. Okay, and I give it a name too. Like this is what people call potential. The total amount of money in your bank account is the potential. Okay, it's the same thing. And then AI, which I call the amortized cost at time I or for operation I, is simply how much you pay per operation. What do you need to pay? You need to pay for the real cost and the payment that you need to put into the bank account, the advance payment. The same thing like before. Like so with this definition, you can see that AI can be written as what do you pay per operation? You pay for the real cost, and you pay for the change in the money in the bank account. Okay. So and the difference of the money in the bank account, I write it as like delta of phi I, like how much phi I change. Okay. And like to interpret this, right? Like you pay for the real cost, that's intuitive. What is this? If this is positive, it's like last time when we make advance payment. We make advance payment to the bank account. This is when the number of like the amount of money in your bank account increase. So this is what you pay. And if this is negative, how do you interpret this? It's like the advance payment, like the money in bank account decrease. So it's like the advance payment you have paid before kind of compensate for the real cost. Like this is kind of how much this money in that bank account decrease, it kind of pay for the real cost. This is what happened when you do link operation in the heaps last time, right? Like sometimes many operation like linking is free. That's when like this thing is decreasing because you use money in the bank account. Okay. But yeah, we're gonna use this formulation now. Like just it's kind of the same thing, but from now when I use the word potential, just think of it as the money in the bank account. Okay? And the potential increase is when you make advance payment, and the potential decrease, it means that the advance payment compensate for the real cost. Okay. And the following theorem is then like with our financial intuition, the following theorem is just kind of trivial. So if phi 0 is 0 and phi I is non-negative, meaning that if there is no initial money and you never have deficit. And if the amortized cost, like the amount of thing that you pay per operation is always at most C bar, then it means that the total cost is at most C bar times operation, so times the number of operation. Okay. This is the total thing that you pay, the total real cost, and this is the total amount of thing that you have paid to the bank account. Okay. I will not prove this because it should be intuitive for you by now, but with the formulation, and if you can use the math to do this formally too, and you can look at it offline. Okay. But my point is, what you need to do when you try to bound the amortized cost is just to bound AI, where AI is just the real cost plus the change in the potential. If you can bound AI, how much you pay per day, you get to bound the amortized cost of the whole sequence or the total cost. Okay. Okay. I can go through this quickly because it's short anyway. Okay. So suppose that AI is always at most C bar, right? Then I'm just gonna write the sum of AI. Let's say that there are capital N many operations. So the sum of AI is here. Each of the AI is just this thing, right? So this is just a sum over C and sum over this thing. Okay. And what is sum of CI? CI is a real cost, real total cost, sum of CI. And what is this? This thing cancel out, like this thing telescope, right? So you're gonna get just minus phi 0 and plus phi n, because they cancel out, right? Okay. And so I just rearrange, right? You get that total cost, then it's just this thing, the sum of AI, plus phi 0 minus phi n, but phi 0 is 0. Phi n is positive. So this is at most. This is just at most 0. And because AI is at most C bar, so and there are n terms, so this is C bar times n. So you get that the total cost is C bar times n. So the amortized cost is C bar. Okay. Let's try to use this potential function method to some toy problem, the incremental counter again, the incremental counter again. Okay. Just to recall, the problem was you have x written in binary, start from 0, keep increasing it by 1, and the cost is the number of bits that you flipped. Okay. So how do you apply the potential function method? Okay. The key step is to come up with the right potential, like last time, where to put the money into, where to put the money on. That is the same thing as saying designing the right potential. And we just said that the potential is just the number of 1 bits, right? Okay. And So you see that. Now let's try to analyze AI. So okay. So AI is Ti plus the potential change. What's T? Sorry, this is supposed to be Ci, the real cost. The real cost is just the total bit flips. So the total number of bits that flip from 0 to 1 and 1 to 0. What is the change in potential? Well, it's going to be exactly the number of bits that is flipped from 0 to 1. This is when each of these will increase the potential by 1. And each of this, the bit that is flipped from 1 to 0, will decrease the potential. So you get -1 here, minus term here. So this is just AI, this thing plus this thing. Make sense? And when you add them up, you see that there are some cancellation here. So you get that this is just 2 times the number of bits that is flipped from 0 to 1. But you know that the number of bits that is flipped from 0 to 1 on each increment, this is at most 1. So AI is 2 at most. And this cancellation here, you see, is just the same thing as when you say that, like last time when we use the money on top of 1 to pay for the cost for flipping. Just the same thing, but presented in a kind of different way. Okay. Any question about this? Okay. All right. So just let me put some word about like intuition about potential. So phi is a total amount of money in the bank, right? How do I think about this? It's also like when you need to design phi, like how do you design it, right? Like potential usually measure the badness, like how bad it is for the current situation. Because like when phi is big, it's like when you need to prepare a lot of money, which means that like in the future you might need to pay a lot. So like if when you try to decide phi, you try to decide phi to like reflect how bad the current state is. Like in the increment counter problem, like the badness of the current state is like how many ones there are, how many 1 bits there are. Because if there are many 1 bits, you might need to flip a lot of 1. Right? So yeah, so that's the intuition. And so why use potential function and not bank account method? Well, you don't need to, but sometimes the proof is kind of easier to verify, and you'll see today how. All right, so I'm just gonna start with maybe we're gonna see two examples today, and maybe one is Splay tree, but I want to talk about another thing first. Another is dynamic edge orientation. Okay. So we're gonna look at another dynamic graph problem. Okay. So before we start talking about dynamic thing, let me start about talking about just the problem, like what is edge orientation. Okay. Just in this problem, imagine that you have a graph, undirected graph, no edge has no direction, right? With n vertices and n edge like before. Now we're gonna look at the orientation of a graph. What is orientation of a graph? It's just like you have the undirected graph and you assign direction for each edge. Once you assign the direction to each edge, that's the orientation of the undirected graph. Okay. So it's just a graph G arrow is just a graph that shares the same vertices and edges. And now each edge of G arrow has direction. Okay. So what's the goal? The goal of orientation usually is to find an orientation such that the maximum out degree is small. Okay. And I'm gonna say that like delta orientation is just an orientation with maximum out degree at most delta. So let's see one example. If a graph is a star, can you find like a one orientation of this graph?
Everyone points.
Everyone point to the center. Okay. What if the graph is a tree? What if the graph is a tree? How do you find one orientation of the tree?
Point upwards.
Yeah. Everyone just point to the parent. Thanks. Yeah. What's your name?
I'm Maxim.
Oh, okay. Okay, sorry. I thought it's...
Oh.
Yeah. What's your name?
Me.
Yeah.
I'm Shishu.
Shishu. Okay, thanks. Shishu. Okay. Good. So a tree has one orientation. And actually, a planar graph, you know planar graph, right? Planar graph is just a graph such that you can draw it without crossing. Like this. You cannot have this. You cannot have something like this. Like the graph that you can draw on the plane without edge crossing. Okay. And planar graph actually has three orientation. I will not prove you formally here, but it's actually like the hint might be fun for you to do this at home. The hint is that any planar graph has at most 3 end edges. And so it means that there must exist a node with minimum degree 3 or something, or 6, yeah, right. There must actually, yeah, 6 orientation. Every planar graph has at most 3 end edges. You can prove this, but if this is true, there must exist a node with degree at most 6. And that's the first hint. And the next thing is like, maybe I just tell you, yeah. So if there is a node with degree 6, then just say that, okay, point everything outward from this guy, right? And then you delete. And once you know that this guy have degree at like outward degree at most 6, then delete this node. And then the rest of the graph is still planar. So there must exist another node with degree at most 6 and point edges 6 edges from that node and repeat. Okay. Anyway, this is not important. The point is there are many graphs out there that actually there exist small orientation. Okay. And why this is a good thing? So there is some simple application. Like suppose that you have a graph and let's say you want to check two nodes U and V whether they are adjacent or not. Whether there is like an edge connecting U to V. Okay. There are 2 standard ways to represent the graph. One is to use adjacency matrix. Right? In this case, you can check if U and V are adjacent in constant time, but the space that you need is n squared. N squared can be much bigger than m, the number of edges, if the graph is sparse. On the other hand, you can also use a adjacency list, where the list is stored in, let's say, binary search tree. And if you do that, okay, you can check if U and V are adjacent just by looking at the adjacency list of U, search for V. That takes log n time. But now, and the space now is linear. So this is good, linear space. And this is good, constant time. Can we do like get the best of both worlds? Okay. Can we get both constant time and linear space? The answer is yes. If the graph has small orientation, like O1 orientation, can anyone tell me how? Suppose that like I give you the O1 orientation already. How can you check if U and V are adjacent in? Yeah.
We could just have the normal adjacency list because it's O1 orientation. We know we have O1 neighbors to check only.
Yeah, we have O1 out neighbor.
Yeah.
Yeah, to check, right? So exactly, like so basically every node, each node store out edges or out neighbor. Each node store out neighbor. List of out neighbors. So the total space that you need here is just like order of n because space is order of n because every node has like constantly many out neighbors. And then how do you check if U and V are adjacent? Well, like there can be like a lot of in neighbor of U. There can be a lot of in neighbor of V. But you know that out neighbor of U and V are small. Like maybe only like not too many. So you can just, and you know that an edge, if this edge exists, it must make U and out, like it must be out edge of one of this guy. So it's enough to like that you just check out neighbor of U and out neighbor of V, and you see that one like if there exists this edge, you will find that U and V are connected. Okay. So you can do actually even or n space if there exists O1 orientation. Okay. So now
Sorry.
Good.
Professor.
Yeah.
Oh, I'm a little bit still confused about how you got from big O of M to big O of N space there. Like, wouldn't if we have this like small degree orientation graph, that would still be big O of M? Or like
It's big O of M, but you now actually see that M is order of N.
okay, that's okay.
Yeah. Right. This is actually the next thing that I will ask you. Can you tell me that suppose that I know that G has C orientation? Can you tell me why the number of edges in the graph must be at most C times the number of nodes? Yeah, Scott?
Because each edge is basically like accounted for by one node's like outgoing edges. And so if each node had the maximum of C, then that would be at most C times number of nodes.
Exactly. So yeah, like each edge is an out edge for some node. But each node has at most C out edges. So the number of edges is then C times the number of nodes. Okay, good. That's simple. Now, if I say that look at the graph here with like a C orientation that has C orientation still. And now I look at any set S, set of vertices, and look at the graph induced by S. So look at only the graph where you look at only edges inside S. You don't look at edge that go out. or outside. Okay, this is a graph induced by S. Okay. Then can you tell me why is it the case that we can say now that the number of edges of the graph induced by S is at most C times S?
S has the same orientation,
Yeah,
at least the same orientation.
right. So basically, like if G has C orientation, in this smaller graph, G induced by S also has C orientation. So the number of edges here is at most the number of nodes, which is just S here. Make sense? Okay, that's also simple. Question about this before I go on? Good. So now comes like something more non-trivial. Okay. So still think of G. G still has C orientation. Okay. Now I look at some orientation of G. This G arrow might be bad orientation, might not be C orientation, might have like some node with large out degree. Okay. But I claim this. Okay, for every node that has like bad out degree, let's say more than 2C in G arrow, okay, this node must have directed path of short length to a node with small out degree in G arrow. Like look at this G arrow. If this node has big out degree, more than 2C, there must exist like directed path in G arrow to X with small out degree. That's the claim. Is the claim clear? Now how can we prove this? This is not that trivial, but basically inverse. How should you interpret this? It means that in any orientation, maybe in a bad orientation, every bad node must have a short path to the good node. That's what I want to say. Okay. So let's prove this. How do we prove this? Okay. I'm gonna define let's look at this node U, right? I will define like a VI. It's just like every node V such that the distance from U to V is at most I. So V0 is just U. V1 is just like a all out neighbor of U, and so on. Okay. And how, suppose that this is not true. Suppose that I cannot find short path to X. Okay. It means what? Suppose that this is not true. Suppose it means that for contradiction, I have that every node X in this set must have large out degree. Right? Because if there is a guy in this set with small out degree, then there must exist a short path from U to X with small out degree. But I cannot find any within my a small region, small this log n a level. There is no node with small out degree at all. Okay, so this is support for contradiction that this is the case. Okay. How do we get a contradiction? First, I claim the following. I claim this. What do I mean here? I mean that if you look at VI, okay, and take all edges that go from VI to some node, okay, some node that may be outside VI. So this edge can be here, can be here, can be here, can be here. Not this one, right? Not this one. Just all edges that start from a node in VI to some other node. This is a set of this edge here. Oh. I claim that all this blue edge, all the blue edges here, is contained in the graph induced by VI minus 1, VI plus 1. And that's kind of trivial actually. This is VI plus 1. This is because, and this is just the graph induced by the VI plus 1. All the blue edges must be inside this graph because, like this edge may be point outside VI, but if it point outside VI, it means that the distance of this node to U is at most I plus 1. Okay. Is this clear? Okay. So we have this. So now I claim the following. I claim that if this is the case, okay, then I know that VI plus 1 is like twice the size of VI. Reason is this. So because we have this, that all edges incident to VI to some other node is contained in the graph induced by VI plus 1. So we have this thing. Okay. And now how big is GVI plus 1? This is at most C times VI plus 1 because we know that the graph G has C orientation. So when you induce by VI plus 1, the number of edges here is at most here. On the other hand, how big is this set? We assume that every node in VI has out degree at least 2C. So the number of out edges incident to VI is at least 2C times VI. This is what we assume. And now you combine these two things, you get that VI plus 1 is twice the size of VI. Make sense? And now you get contradiction now. Why is that? Because when you increment I by 1, the size double. But now you're gonna double like a log n plus 1 times. But that means like the size of V log n plus 1 is like 2 to the log n plus 1. But that's like more than n. But there are just n nodes. So that's impossible. Okay. So now we have this. Okay. Every bad node has some short path to a good node. Okay. So we have some structural understanding of the problem a bit now. Now let me talk about what we want to do today. Okay. I want to solve this problem. The problem is that I have a graph like before, undirected graph, but this graph now undergoes both edge insertion and deletion. I might insert one edge at a time, delete some edge at a time. Okay. But I promise to you that at any time the graph has C orientation. Think like the planar graph is updated. So as long as your graph is planar, there exists like a 6 orientation, for example. So this is like some promise that you can have. Okay. Now, okay, what we're gonna show today, we're gonna look at 2 algorithms. One algorithm is we're gonna try to maintain 2C orientation. So a bit worse than C. Okay. We're gonna maintain 2C orientation undergoing this edge update. All the out degree is at most 2C. Okay. And we're gonna do it such that the worst case flips the number of edge. Like when you update the graph a bit, you might need to flip direction of your orientation. And the worst case number of flips is just gonna be something like log n per update. But this algorithm have, like, you don't need to flip too many edges, but it's quite bad because the time to actually flip this is linear. You kind of need to read the whole graph. But then you're gonna see just another algorithm that a bit worse, not 2C but 5C orientation, maintain this one. But now the amortized cost is actually log n. So let's do this two algorithm one by one. Okay. So anyone have some idea about this actually before I even tell you? We're gonna use this for sure. Okay. Yeah.
Well, this is like just like a starting point, but
Yeah.
there are bad nodes and good nodes, and if we have a path from a bad node to a good node, then if we just flip every edge going from the bad node to the good node, it's making the good node worse, but the bad node better, but it's kind of like evening everything out.
Yeah, very good. So like imagine that like you have a path from bad node to good node and you flip the direction of all this guy. What's the change of degree of our degree on the guy in between?
0.
The same. It's the same. But the out degree of bad guy now decreased by 1. The out degree of good guy increased by 1. So this is like a good idea now. So it means what? If you have a graph and suppose that you already maintain 2C orientation, you have it with you. If I delete an edge, what do I need to do? Nothing. It's still 2C orientation. It only get better. But now when I insert an edge, let's say I orient an edge in some way, I don't care. Okay? But when I orient this newly inserted edge, maybe now some node has increased its out degree. The out degree of that guy now can be what? 2C plus 1 because I just insert one edge. So that is like, suppose that is bad. Like if this happened, that is the bad node. Call that node U. Okay. So this is the bad node with degree 2C plus 1. And we know that there must exist a path, a short one to a good one. So flip the path. Now this guy will have degree what? 2C. Because it's decreased. This guy still have degree at most 2C because it was strictly less than 2C. So now we are done. So you see, this is the whole algorithm. But why is it bad? Because it's not clear where the good guy is. Like you might need to do breadth first search for the whole graph. You cannot just like know that okay, this is the path and just go along that path. No one tells you where X is. So you might need to do the whole breadth first search, and that might take you linear time. Okay, so that's bad. What's bad about this algorithm? Question? Yeah.
Could you improve the time by somehow like storing information of like where the nearest good neighbor is?
That might be a good, that's a good good like a suggestion. I'm not super sure how to do this in an easy way because you see, suppose like this node, you store a good node X.
And then you like delete the path to it.
When you delete a path and like this path kind of now, I don't know, we need to update X. Yeah. Okay, so that's a slow algorithm, but the number of flip per update is small. In the worst case way, actually. Okay, so now let's get to the better algorithm. Okay. The better algorithm is here. Now it's going to be fast. It's just an algorithm that when you delete an edge, do nothing like again. It's only get better. And when you insert an edge, assign the direction arbitrary again. But now, whenever the X is a node without degree more than 5C, I reset. What do I mean by that? I just flip everything out of me. No, into me. Yeah. Just make it such that like my out degree is 0. So, like it seems like I don't really think much. Like I'm super bad, so I just make me good. Yeah. Okay. That's it. That's the algorithm. The correctness is trivial because whenever there is a node with out degree more than 5C, I just improve that node. But the running time is unclear, right? Because when I like reset the node W, I might cause another node to reset. And when I reset another node, it might cause another node to reset, and so on. How to analyze this? So the worst case cost can be bad. But we're gonna see that amortized cost is actually really good. Okay. So my claim is this. Suppose that Ni and Nd is the total number of insertions and deletions, like the number of times that you insert and number of times that you delete. My key claim is that the total number of times that I'm gonna reset is gonna be bounded by Ni times like log n over C. We're gonna prove this soon, but assuming this, what do we have? We have that the total update time throughout the whole algorithm is the following. When you delete, each deletion you spend constant time. Each insertion you also spend constant time to insert. And you're gonna do some reset. But for each of the reset, how much time do you spend? You spend like a C times, right? Like you flip like a C many edges, right? You used to have out degree 5C, now flip so that you have out degree 0. So flip C edges. Okay. And if the number of reset is like a Ni times log n, then this thing is just Ni log n. So sum up this, you get that the total time is Ni times log n plus the Nd times 1. It just means that the amortized insertion time is log n, amortized deletion time is 1. It's all 1. So it's just like a boils down to prove this thing. Why this is the case? We're gonna use potential function or bank account. Think of whatever you like what's like easier for you to think about. But how do I design potential function? Okay. I'm just gonna design first I'm gonna define an edge to be bad. An edge is bad if the slow and fast algorithm assign different directions to E. So note that I'm just run my fast algorithm. I don't even run my slow algorithm. The slow algorithm now is just purely in analysis, right? Just imagine that there is some slow algorithm that you don't actually run, but the slow algorithm will assign direction of edges somehow. And we're gonna say that that edge is bad if they like a fast and slow algorithm disagree. Okay. Otherwise, it's good. If they agree, then it's good. And the potential function is just a number of bad edges. Okay. Okay. So now I claim this. The total increase in the potential, like the total money that you put in the bank account, or like the total increase of potential, is at most this one, Ni times log n. Why? Because for each deletion, clearly you don't increase the number of bad edges, you delete edge. How about insert? Okay. When you insert, okay, you might increase one bad edge by one, like that's the inserted edge. But you know that the slow algorithm will flip log n edges. For each flip that is done by the slow algorithm, that might increase the number of bad edges. So how many of that flips? It's like log n plus 1. Yeah, Guy.
Why is that bound to the amount of flips that we can do with the fast algorithm? Because if the fast algorithm like kind of cascades the whole graph, but the slow algorithm only flips log n, why aren't all the ones with the fast edges flips if the slow edges doesn't? Why aren't those bad edges?
So right now we are not trying to like say that the number of flip by fast algorithm is like is small in the worst case. There can be some time that the number of slow algorithm, our fast algorithm actually flips so many. But we're gonna say that in total, actually it's like we've flipped not too many in amortized sense. And how do we do that? We're gonna go through like some like amortized analysis here. Okay. So right now, let's like just think only about this potential right now. Okay, and right now just try to agree with me that the potential can increase per, like for one insertion, the potential can increase at most, okay, good. I see what you mean now. Let's think of insertion, one insertion, and let's say the fast algorithm don't flip anything yet. Okay, yeah. We don't do any reset yet. Look at the time when the slow algorithm flip the path, and we don't do any reset yet. At that time, the total increase of phi is just log n. You agree with that, right? Okay. So that's how much you increase the potential. But now I claim this. I claim that whenever you call reset, you actually will decrease the potential by C. So let's see why is that the case. Okay. This is my claim. This is because when we reset, the out degree of that node that we reset is more than 5C. Okay. Among these out edges of U, like look at this, we're gonna flip. There can be like many other in edges, right? But we're gonna flip this guy, 5C of them. Among the guys that we flip, how many can be good? The good one can be at most 2C. Because the the good one agree with the slow algorithm, but slow algorithm has the slow algorithm maintain 2C orientation. So the slow algorithm can have out degree at most 2C. So there can be only 2C that is good, 2C that are good. Everything else are bad. So the bad guys that are at least, sorry, this should be 3C, many bad guy. Okay. Among 5C of flip edges, only 2C can be good. So at least 3C are bad. Okay. Then let's think what happened when we flip these edges. When we flip the good one, the potential will increase, right? They used to agree, now they disagree. But when we flip the bad guy, they become good. So the potential will decrease for each of for each of this flip. So it's gonna increase by 2C but decrease by 3C. So in total, when we flip all this guy, the potential will decrease by C. Like it's like a increase by 2C but minus 3C. So this is like a decrease by at least C. So you agree with this, that each reset will decrease the number of bad edges by at least C. Okay. So it means what? Like the total number of increase in phi is at most this, and the total number of decrease is like this much. So we get that number of reset is just this thing Ni over C. Questions about this? Yeah.
If you theoretically had like a slow algorithm that maintains C, could you just do the same exact thing but with 3C?
Exactly. Yeah. So yeah, you can like, yeah, that's exactly. So if you know that like this is at most C, then you can just say that this is 3C and this is 2C, and everything gonna work. Yeah. Okay. Question? Okay. So let me wrap up. So you see that the fast algorithm takes total time, something like reset times C. To say that like the number of reset is small, what we did is like we defined a potential function such that the total increase is small, but every reset the total increase in potential is small. It's bounded by n log n, like insertion times log n, but each reset will reduce the potential. So because of this, then there cannot be that many number of resets. Okay. And we don't actually run the slow algorithm. We just use it in our mind. Okay. So you can try at home to improve this constant 5. I believe you can go to something like 3, maybe better. Okay, good. So that's one topic. The next one is Splay tree. Okay. This is one of the magical algorithm from like 40 years ago. I want you to learn about this. Okay. So everyone know binary search tree. It's just a tree such that for every node, like everything on its left is smaller than itself, everything on its right is larger than itself. Okay. And it can do a lot of things, but today let's say we're gonna look at one operation, look up, just search for an element. Okay. By the way, like one way to think about binary search tree, I'm not sure you have thought about it in this way, but this is the way that I think about it. So like, suppose that it store, like the binary search tree store many numbers, right? Like can be like any numbers. And let's say that we write the number from left to right in the increasing order, like 1, 2, 3, 4, 5, 6, and so on. And once I write the number from left to right by its order, and then let's say that I specify the relative depth between them, like which one should be higher than which one. Like this one is the top, is the highest. This one is below, and so on. Once I fix the height of every node and I fix the order, then the structure of binary search tree is actually determined. It's unique. Why? Because like if I say that, okay, this node need to be the highest, then this is gonna be the root. Okay? And then within this, everything on the left and on the right, if this guy is the highest among everyone here, then this is, the root must connect to this guy. And 14 must connect to 22. And can you tell me what should be the children of 22? Yeah, Guy.
20 and 23.
20 and 23? No. 23, yes.
16?
16, yes.
Okay.
Right. So like everyone on the left of 22 is here. This guy must be the highest. So you connect this guy and this guy. Okay. So basically, I hope you see that like once you fix the ordering and you fix the relative height, you can actually forget about the edges of the tree. It's fixed.
Are all valid like depth specifications, are all depth specifications valid?
Yes.
Or
Yes. Any depth specification is valid because as long as like they have distinct depth, right? When you have, let's say they have distinct depth, the guy with the highest one is going to be the root. Then you just look at on the left and on the right, who is the highest? Then you connect to that. So any order in height gives you the valid tree. Okay, so this view is clearer to me because like I usually don't like to think of binary search tree of edges. It's just like a point on the plane. Okay. Okay, and you have seen that okay, optimal BS tree has like a worst case time log n, but you can do better. Like you did in like we did this for like using dynamic programming, right? If we know like a distribution of how we access things, then sometimes unbalanced tree is better. Because if you access one many like so often, then this is better. Okay. But okay, we know how to design the best binary search tree if I tell you the information, what's the distribution, how often I access each element. What if we don't know that distribution? Knowing distribution is like a kind of assuming a lot, right? What if we don't know that? Okay, if we don't know that, we cannot use DP. So the ambitious goal that we're gonna show is that I will actually show that like Splay tree is the algorithm that kind of automatically learn this search probability in the sense that like it's amortized cost. It's gonna be like the cost of optimal BS tree. Okay. Like, you understand the claim? Like, if suppose that there is some unknown distribution of among elements, you could design the optimal binary search tree for that using DP. But if you actually don't know that, but if you just run just use the same access, but do it on binaries like on Splay tree, the one that I'm going to describe, the cost of Splay tree actually is going to be as good as the one that you design using DP, although you actually don't even know the distribution. But the cost is going to be good up to constant factor. It's not like exactly optimal, but within constant factor. Okay. So this is already impressive, but actually it go much more. Splay can do much more. Okay. So let me tell you what is Splay. How many of you have seen Splay tree? Okay, good. Then you learn it today. Yeah. Okay. So the first thing about Splay that you need to know is rotation. You know rotation. Okay. But I want to tell you that rotation, like with the view that I just told you, like that binary search tree is really just a point, like a bunch of points on plane. Okay. Rotation with this view is actually quite simple. To rotate between x and y, it just means that you switch the height of h and y. You switch the height. And then just try to connect them in the unique way that you need to connect. How do you connect this in a unique way? Then it just need to be this way. Okay. But you don't need to think about how you point the pointer and change the pointer and so on. Just switch the height. That's how you think about rotation. Okay. Now that I described rotation, I can tell you about Splay. Okay. Splay is this. Like basically, the algorithm is like whenever you want to look up some element x, we're gonna Splay x. But what is this? This is to kind of inverse. It's like to rotate x to root. Try to move x to the root by looking at like a 2h at a time. There are 3 cases to look at. Let me tell you. So suppose x is here, okay? And if its parent and the grandparent are on the same side, here it's like on the left side, on the right side of you. Yeah. It's on the same side. Yeah, right. Then what we're gonna do is just previously the height of x is less than the height of parent, which is less than the height of grandparent. You're just gonna rotate make it such that x is higher than p and p is higher than g. Once you do that, connect in the natural way, in the unique way. This is sig. When grandparent and parent are on the same way, on the same side, just make it like this. Okay. The next case is when the grandparent and the parent are not on the same side. What you do is just you move x to be above both of them. That's zigzag. Okay. The last case is when there is no grandparent. Then you just rotate. Just move x above the parent. Okay, let's see some example. Like basically, if x is here, then we all the ancestors are on the same side, but then we keep doing zigzag. So we're gonna do zigzag like this. Do zigzag, and then look at the parent and the grandparent, and then zigzag, grandparent and parent, and zigzag. That's it. And if it's here, like we keep doing the zigzag, do this, and do it again and again and again. And last time here, you need to do 6 because there's no grandparent. Make sense? Okay. So let me show you how it works in real life. I don't know, in the simulation. Like you might start with this kind of tree, right? That is really, oh, sorry. Okay. You might start with this tree that is like really unbalanced. Let's say that I access this. Then you get this. Maybe I access this, you get this. And you see like it's just kind of balance itself pretty quickly. Okay. Yeah. Can you tell me what's the worst case lookup cost for this? Yeah.
Just ON when it's a stick.
Yeah, it can be ON because that can like you can make it such that it become like unbalanced. For example, I just keep accessing like from 1 to 0, from 0 to n. I can make it unbalanced like this. But you see, I need to make a lot of effort to make it unbalanced. But if I say I do this, now it's kind of balanced again. So yeah, so it's pretty nice. Okay. So worst case cost is bad, but amortized cost is going to be good. Okay. So the key lemma is this. I claim that this is not easy to pass, but let me tell you. Okay. The key lemma is that if you fix any weight function that you can imagine of, like any weight function, right? This weight function might not have nothing to do with whatever, like just some weight function. Okay. Here, that map the key to some positive number, and then you assign that capital W to be the sum of the weight, the total weight. Okay. Then the amortized cost, the amortized time to Splay X is going to be W, like log of W over Wx. Okay. What's the, like I'm going to prove this, but it's non-trivial. But what's the implication of here? Implication is that let's try to apply this lemma for different weight function and see its implication. Okay. So if I just set W to be 1 for every key, then like capital W is n. It means that the amortized time to Splay any node is just gonna be, this is gonna be n, this is gonna be 1. So it's log n. So it means that in amortized sense, like Splay tree is as good as like balanced binary search tree, like red-black tree, AVL tree. Okay, so that's like a quite good now, but it's actually better if X is searched with probability pi. If Xi is searched with probability pi. Okay. Then the expected cost of optimal binary search tree will have this cost. Like we actually do DP to do like to get to some like the optimal binary search tree, right? But I will not show you the proof, but actually that the cost of that optimal binary search tree is going to be something like this. Within constant factor, it's going to be this thing. Okay. I'm not sure you have seen this, but it is called entropy of the distribution. Okay. It's a good concept you can look up, but not for today. Anyway, this is actually like up to constant factor. This is the cost of optimal binary search tree that you do it using DP. But suppose that we gonna try to analyze the cost of Splay. Okay, and I just set the weight of xi to be pi. Okay, so the total weight is 1 because sum of pi is a distribution, so sum of pi is 1. So it means that the amortized cost for splaying the xi element is going to be log of w over this, which is log of 1 over p, which means that the expected amortized time is here. So it's just matched with the one you get from DP, although we don't know the distribution. And the point is like, actually it's competitive to any distribution. Like you see, like I don't even know the distribution. I can just put the distribution here to like put pi, set it as a weight. I can put the weight of x to be some other distribution too. So it's like not just competitive to the best algorithm for one fixed distribution. It's competitive to every optimal algorithm, every optimal binary search tree for any distribution. So it's pretty crazy. Okay. So yeah, intuitively it means that for any sequence, the cost of Splay is constant times the cost of optimal binary search tree with respect to the sequence. Splay is oblivious to the sequence, but it kind of adapt to the sequence. Okay. All right. So now I will need to prove the lemma. Okay. What does it mean to show that the amortized cost is here? Recall that like it means that I just need to come up with a potential such that the amortized cost is the real cost plus the potential change. Like the amortized cost, which is the real cost plus potential change, is this thing. If I can come up with potential and analyze that this is the case, then I'm done. Okay. And the potential is crazy. Okay. It's this. We first need to define the rank. Okay. The rank of x is log of the total weight in the subtree rooted at x. So meaning that if this is 3, if this is x, look at the subtree here, call it tx. Then this is like, what is this rank? Is like a sum of every u in tx, the weight of u, and then take log of that. And the potential is the sum of the rank of every node. Not clear why we want to define it this way, but is the statement clear? Okay. Okay. Okay, good. So now let's analyze one thing. What happened when we do zig-zag? Okay. I will just analyze how much potential change. Okay. And claim is that the only guide that like the change in potential is because of the change of the rank. But I claim that the rank of every node stay the same except the rank of x, p, and g. Because the rank of any guy below x, p, and g here like the rank just depends on the subtree below it, right? The rank of everyone here stay the same. The rank of the guys above, like the guys above, the grandparent of the above G, stay the same too, because from the perspective of maybe this guy, Y is here. Here, like you kind of just rearrange something in its subtree, so the rank of Y wouldn't change, right? So you see that like it's really just the rank of X, P, and G that change. So the change in potential is just like how much the rank of G change, how much the rank of P change, and how much the rank of X change. Okay. And now we'll need just to calculate a bit. And I will not go through all this calculation because it's calculation. Okay. But I claim that we're gonna get this -1. Okay. So let me try to do something like explain a bit why. But this -1 term here is going to be very important for us because when you compute potential change and you get negative term, it means what intuitively? It means that this advance payment, this is an advance payment that compensates for the cost, right? Each negative term in potential is like our advance payment pay to us. Okay. Okay. Since I don't have much time, okay, let me still do, like I need to do one thing. The reason why we get -1 here is because of this thing. This inequality, and it means that like a log of A plus B is at least if you take log, right? Yeah. It means log of A plus log of B plus 2. Okay. And now, okay. And now, if I think of this and here, then it means that call this A, call this B, and call this whole thing C. This is A plus B. No. So the old rank of X is basically A. The new rank of G is B, and the new rank of X is at least it's like log of A. This is log of B. This is log of A plus B. Make sense? Like this is just a total weight of this subtree. I let B be the total weight of this subtree, and so the rank of X, the old rank of X is log A. The new rank of G is log B. The new rank of X is like at least log A plus B. Okay. So it means that now it means that 2 rank of X, like use this thing here, is at least rank of X plus rank of new rank of G plus 2. And I let you calculate this at home, and you're gonna get this thing. Sorry, I don't have much time. Yeah. But it's about calculation. Yeah. And when you do 6, you're gonna get something like -1 here as well. When you do 6, you don't get -1, but you get like this thing, like at the end of the day, you get like the change in potential is like new rank of x minus the old rank of x times some constant and minus 1. Okay. When you do zigzag or zigzag, you get the minus 1. And that's important. Why is that? Because now imagine when you do the whole splay. Okay? When you do the whole splay, what do you get? You do one splay, like one zigzag. The change in potential is like increased by this much, decreased by this much, and you get minus 1. That minus 1 is like is compensate to pay for doing yours to perform zigzag or zigzag. You use that minus 1 to pay for this thing, to pay for the real cost here. And you do again, you do another zigzag or zigzag, you get increase of here and decrease of here. So this thing cancel. And do again. At the end, like you're gonna get like plus rank of the root minus rank of x. And for every step that you do zigzag or zigzag, that's free, because you get that minus 1 for free. There is one last time that you do zigzag, you do zig for the last step, but that's only happened once. So basically, the real cost, like the cost that you get at the end, how much you need to pay, is just like this much minus this, and plus constant. Okay. So this is like the total that you pay. It's just the rank of root minus rank of x plus constant. And what's rank of root is just rank of like a log of w. Rank of x is minus rank of weight below x. So this is just like you can write it this and you get that this is O of log of the weight, the total weight over weight of x. Okay. So that's basically give us the excess lemma that implies a lot of cool things. Okay. So let me summarize. You see, with our potential function, it's so hard to actually prove this thing. Like you have bank account method, but like this, it's hard to talk about like where is the dollars and so on. Like so sometimes the potential function is kind of stronger to think about. And it's non-trivial to come up with the right potential. Like you see, it's like the sum of the rank. You need to get like a really good intuition about the system to come up with the right potential function. And yeah, like this is the topics about amortized analysis. And next time I'm gonna mention some really nice open problem. But yeah, for today that's it. And like next class we'll focus on randomness, randomized algorithm.